Hello. My name is Simon Gerst. I'm a security engineer at Asymmetric Research, and previously I was a computer science student at KIT. Much what I'm going to talk about is born out of research I did at my studies. And in a high-level nutshell, I wrote a tool to automatically find some bugs in the JavaScript engine V8 in a very specific part of the code. And then I use those counterexamples I get to automatically generate JavaScript proof of concepts. So first, a bit of motivation. We have this very simple JavaScript code. And, one second. This very simple JavaScript code, which just checks whether x plus y is bigger than 10.1. And if this is the case, we execute many instructions. And every user of a browser or JavaScript engine, of course, wants that their code is executed as fast as possible. And how do we do this? In this specific case, we could remove the if statement because it's that code, and by removing it, we lessen pressure on the instruction cache and speed up compile times because we have to do a lot of less stuff. So remove this, and this transformation, I guess everybody would agree that is obviously correct. So yay. And in this case, for the simple case, we can identify that code using constant propagation. We can just substitute for x 1.4 and for y 2.3, then we can perform the addition and perform a comparison. And then in the end, in the if condition, we have an if false, which clearly means that the code is dead. And for more complex cases, we can use something that's called range analysis. And this is what I'm going to focus on. And with all analyses, you have this kind of trade-off. You want a powerful analysis so that you can optimize your code as fast as possible. But in the JavaScript world, it's very important that your analysis is also correct. But if your analysis is powerful, it tends to get more complex, and complexity makes it harder to be sure that it's correct. And the more complex, the slower your analysis is usually. So you have this trade-off. And for example, we slightly changed the example so that x is either 1.4 or 5, and y is either 2.3 or 5. And let's, for example, we have an analysis, and this analysis says, hey, our if condition, it's that code again, and removes it. And obviously this information is wrong, because just looking at y, we see that 2.3 is obviously greater than 1.4, so this if condition is true and not that code. In the context of JavaScript, even very small correctness issues can lead to security vulnerabilities. There was a case in the past where they were missing a special floating point case. Like for floats, you have a positive 0 and you have a negative 0, and developers they missed the negative 0 case, and this single case was enough to completely exploit the JavaScript engine. So as an outline, I want to give a quick background on JavaScript and doubles, what is bond model checking, which I use as my formal verification tool, and then my work, which focuses on the verification of range analysis and what it means for an analysis to be correct. I will explain my system that I built, the harness I built, so that I can use bond model checking, and then my automatic test case generation, which goes from the counterexamples I get to an executable JavaScript proof of concept. And as this was an academic work, or I would say every work should have an evaluation section, and then I conclude with a conclusion. Okay, so we as a user, we want to execute our JavaScript code. And so what is JavaScript? It's a high-level dynamic weakly typed language. It has only a few fundamental types: strings, objects, numbers. And this gives some performance challenges. You have weak typing and implicit type conversion, dynamic typing. So for example, if you do x plus y, this can be pretty expensive because you do not know whether x is a string, an object, or actually a number. And this leads to pretty inefficient code in a general case. And the key solutions are just-in-time compilation and type feedback and speculative optimizations. And every big JavaScript engine implements this. V8 implements this for Google Chrome, SpiderMonkey for Firefox, and JavaScript Core for WebKit. And I will focus on the V8 engine, which has about 1 million lines of code, and it's already extensively secured tested. There are teams focused at Google working on V8 the whole time on security of V8. There is external researchers. They run a bug bounty program where they pay a lot of money for researchers to find bugs. And so it's a pretty hardened target. So finding like any bug in it is like an achievement. Okay, so we have our JavaScript code, and first it gets interpreted by an interpreter, and during the execution, the interpreter collects type feedback. For example, if we call a function x plus y, and we only see actual integers for x and y, we can use a cheap integer addition instead of, for example, specializing for a string concatenation. And then after a while, we realize, hey, this function is called like thousands of times. Maybe we should just-in-time compile it so it can execute even faster. And in our case, it is done by Turboshaft, which has various analyses, that code elimination or also range analyses. And the end result of this is machine code, which is as optimized as possible. And the interpreter together with Turboshaft is what is called the V8 engine. And if you know V8 in a bit more detail, there are also other parts of it, but they are not relevant for my work. Okay, JavaScript uses doubles as their main number type. Recently they added also big ints, but still doubles are the main number type. And what is the most important part of the slide is that there is a sign bit. And the result of this sign bit is that you can have a positive 0 and a negative 0, which is a bit unusual. And you also have another special value, which is not a number value. Which you get, for example, if you try to do the square root of -1, which is not defined, so you get not a number. And what is often surprising for computer scientists is that many known rules don't work. You cannot expect 1.0 added to 1.2 to be equal to 1.3, or even something as simple as multiplying y times 0 is not the same as 0. Because if y is not a number, then the result has also be not a number and not 0. Or a plus b, parentheses a plus b plus c is not the same as a plus parentheses b plus c. So a lot of the known rules don't work. Okay, now on the range analysis in V8, and the high-level goal is like I want to verify that the range analysis that V8 performs is correct. And for that I use ESBMC, which is it's a bounded model checking tool, a form verification tool. And the purpose of range analysis in V8 is it tries to determine the possible values for variables or for numbers in relational operations. For example, in this case, and the role-in optimization is for that code elimination, which will lead to more efficient machine code. And V8 uses something that's called abstract interpretation, and every expression has an abstract representation. And it's getting a bit more technical, but bear with me. And you have something called ranges, a, comma b, and something called sets, a, comma b, comma c, and then they can these tilde, -0, tilde none means that you have a union. So either the value can be in the range from a to b, it can be the special -0 value, or it can be the not number value. And in this case, if we want the abstract representation for the variable x represented as a range, it is 1.4 till 5, because x is randomly chosen to be 1.4 or 5. And so if we generalize this, we get this range. And similarly for y, the range is 2.3 to 5. Now, if we want the range for x plus y, we have to add the lower bound of the x range to the lower bound of the y range to get the new lower bound, and the upper bound similarly. So we add 1.4 to 2.3 to get 3.7, and we add 5 to 5 to get 10. And now we want the abstract value for our comparison. And in this case, we know that it is false, because the maximum value of x plus y, as can be seen by the range, is 10. And 10 is obviously not bigger than 10.1. So it is false, and we know that it is dead code. And we can also do this with sets, but in this case we get to the same result. And V8 implements this abstraction function by a dedicated addition function. And there's like one abstract operator for each concrete operator. So you have like your concrete addition and you have your abstract addition. And if x and y are sets, you just do like a Cartesian product and apply the concrete operator on every product. And if you have ranges, then you use something called interval arithmetics. And for interval arithmetics, you can, for example, look at Wikipedia or your favorite math paper to find the basic rules. And for addition, for example, as I already mentioned, you take the lower bound of the two ranges, add them, and you get the new lower bound of the result range. For subtraction and multiplication, it's a bit more complicated, but this is for like normal integer numbers. But we are dealing with floating point numbers. And so, for example, we add to x minus 0 and not a number separately. And there are a lot of edge cases for not a number and minus 0 in the specification. And your simple rule for addition, it doesn't work with floats anymore, because you get like problems with the number. And why am I even looking at this? I'm looking at this because there were 3 bugs in the past in abstracted ranges. I found one of those bugs myself using manual code review. And every good security researcher knows if there has been a bug in the past, there's probably another bug, as we've just recently seen. And I focus on abstract ranges because they are more complex than abstract sets. Okay, so what does it even mean for like a range analysis to be correct? Let's say we have 2 ranges, left, right, and result, and then we pick any value x which is contained in the left range. We pick any value y which is contained in the right range, and then we pick the result of x plus y is c, which is from the result range. And then what does this mean that it is correct? The analysis is correct if for all, if I pick any value x and any value y, then the result c always has to be contained in the result range. It is not allowed that the result c is outside of the result range, because in that case, things will go bad. And now a bit more formal definition. We have a left range, a result range, and a right range, and we get the resulting range by applying our abstract operator, for example, our abstract addition to the left and the right range. Then we have concrete values x, y, and c, concrete floating point values, where we get c by applying the concrete operator x to y. For example, like concrete addition, we add x and y and then we get c. And if the x value is contained in the left range, the y value is contained in the right range, then it has to always hold that the result is actually in the C range. Because if it's outside the C range, then we have a bug. And now I have to talk a bit about bundle model checking, because I've used it to do this verification. And basically the goal of automated model checking is to find bugs by checking if a program can reach a state. You have some starting state, and then you can transition to another state, and basically what we're trying to check is whether I can go from the starting state to some bad state, for example, an assertion error. And it works in basically 3 steps. You translate your program into a large mathematical formula. Then you add the condition you are looking for, your assertion. And finally, you use an SMT solver, or you can also use a SAT solver to find inputs that make the formula true. And here comes the bounded part. Generally, you cannot translate loops into your formula, or I mean you can, but then your SMT solver cannot solve it. So you unroll your loops a certain times, which is called a bound. And this is a trade-off, because you now can only be certain that you have found all bugs within your loop unrolling bound. But if you know that you have unrolled every potential loop often enough, then you can also prove that your program is bug-free. Like for example, if you know that every loop only is executed at most 10 times and you've unrolled it 20 times, then you can be sure that all loops have been accounted for. And for example, the simple code is addition. We just generate a formula which says that the return value of the sum is the same as a plus b. This gets a bit more difficult if you have multiple assignments. If we have y is x times x and y is y plus x, then how do you model it? Y is equal to y plus x. There is no time in your mathematical formula. It doesn't know that one instruction is executed before another instruction. And so your solution is something that's called SSA, which means static single assignment. And every assignment to your variable can only be done once. So you have one assignment to the y1 variable, and if you want to assign to the y variable again, it has to be like a new variable. And so the first y in your y equals y plus x is now y2, and the second one is y1, and so you don't have a problem anymore. Now you also have a problem with control flow. Like if you have this function which computes the maximum, you use something that is called phi nodes, which are basically implemented like this. You have a bit which evaluates your condition, and then the phi node chooses either the first result or the second result based on whether A is smaller than B. And this can then be converted to your formula. And if you would, for example, add this assertion, which is wrong, this assertion is wrong, that your result is always less than A, you would simply add another logical conjunction to your formula. And then you give this whole formula to your SMT solver, and if it can be solved, you get a counterexample, and if it cannot be solved, you know that your piece of code is safe. And if you didn't follow everything, that's fine. That's not that important for the rest of the work. But I just wanted to give you background. Okay, so we have our range analysis, and the main way to interact with the range analysis is, of course, using JavaScript code. The JavaScript code is interpreted and then given to range analyses. And what I now want to do is I want to interact with the range analyses from my own code. So as a user, I execute my ESBMC, which is a bounded model checking tool, and this then verifies a special verification harness that interacts with range analyses in the engine. So for example, we want to verify that the abstract operator for the division is correct. And now the problem is that the ESBMC tool, it cannot directly execute the function. So similar to like a fuzzling harness, I write a bounded verification harness, which first implements the correctness formula, so the assertion that I want to check, and that drives the division function. And then we implement like for all quantifiers using non-deterministic assignments. And now either we get the result that the code is correct, or we get a counterexample. And in this case, we get like a trace which contains all states up to the failing state, and we get concrete values for our ranges and concrete values that should be contained in the ranges. So yeah, we either get the counterexample or we get a correctness witness. But now we kind of have a problem because I've interacted with the analysis using C++. And if I now go to the V8 developers and say, hey, run this tool and the C++ file, they will like, yeah, but our users, they don't interact with it using C++. All they do is running JavaScript code. So what I want to do is to take this counterexample, which is like based in the C++ world, and automatically generate a JavaScript file that can then, when it's being run again, will trigger the same crash as I found using ESBMC. And this is a two-step approach. First, of course, I have to extract the ranges and the concrete values from my counterexample, and then I generate the JavaScript code such that when the JavaScript code is again executed by the JavaScript engine, the range analysis operates on these exact values. And I did this in some template pattern way. And the main idea is that V8, as again, it has two representations for the abstract operations, sets and ranges. And V8 converts sets to ranges for sets that have more than 8 elements. So if you already have an element, already have a set with 8 elements, and you try to add a 9th element to the set, it will get converted by V8 to a range. And using this, we can generate any floating point range and also handle not number and -0. Unfortunately, some ranges have insufficient distinct values for conversion because the 8 values in a set have to be distinct. So in this example, you have to range from 1 to 1 plus 2 to the power of -42. And in floating point math, there is no distinct value between those two values. So yeah, we have 2 distinct values, but we need 8. What are we doing? One idea would be to like scale the whole range. So it becomes 8 and 8 plus 2 to the power of -49. But this does not work because due to how floating points work, there is still no distinct value between the lower bound of the range and the upper bound of the range. But what we can do, we can split our range into 2 ranges. One range which is 1, and one range which is 2. One range which is 0 to 2 to the power of -52. And then what we are doing in the code, we just add the 2 ranges, and if we add the 2 ranges, we get back the range we wanted to produce earlier. Unfortunately, and this works because there are enough distinct values between 0 and 2 to the power of -42. But again, there are also edge cases. In this example, there are no distinct values between 0 and 2 to the power of -1074. So what can we do? In this case, we can actually scale, because the 0 remains unchanged, but the upper bound will get changed, and because upper bound gets changed, we gain new distinct values between the upper and the lower bound. And this allows us to get a range, and afterwards we can just undo the scaling, which will keep it as a range, but which will allow us to create our original range. And yeah, I'm not sure whether you are convinced that this works, whether it's correct, and I myself also wasn't really sure whether I have handled all edge cases or whether there's something still missing. So I wanted to do formal verification on my automatic test case generation. So I implemented it in C++ and used ESBMC again to verify it. And yeah, turns out there are 2 bugs. I forgot to handle a case with infinities, and also ESBMC's modeling of a specific floating point function was incorrect. And yeah, full verification takes a bit of time, but now I'm confident that my approach can handle every edge case. And this allows us to get full circle. We start at the bottom with ESBMC with our C++ counter example. We generate a JavaScript proof of concept, and this proof of concept can then be executed by the interpreter, and finally it will end up in Turboshaft range analysis, where it will then cause a crash, which is the same crash that we indirectly found using our verification harness. So yes, as I said, every academic work has an evaluation. So my research questions were, can I find new bugs? Can I find some old bugs, like the 3 old bugs I mentioned? And can I also find some synthetic bugs I inserted myself? Can we maybe prove that the operators are correct? And also what was interesting was to look at different SMT solvers. Maybe there's one which is the most efficient. And yeah, I had a very beefy machine, usually a time limit of 8 hours and 100 gigabytes of RAM. And yeah, quite a few different SMT solvers. So first I evaluated on a new commit. This commit is from December 2023. It's the last commit before there are C++20 requirements, which the ESBMC tool cannot yet handle. And the range analysis code itself has been unchanged since this commit, so this is fine. And yeah, I was lucky enough to find a new bug in the range analysis. And again, the division, I think all the 3 bugs handle the special -0 edge case incorrectly. And my new finding also finds that they handle another edge case incorrectly. And the bug has been confirmed by the VA team and is currently being triaged. And depending on the solver, you can find this bug in less than 5 minutes, or maybe 8 hours, or if you're unlucky, you get a timeout. I don't really know why SMT solvers are so different, but I guess it depends whether maybe some explores a path earlier that is maybe harder to reason about. And in some, the Bitwuzzler solver is the fastest across different bitnesses, so it doesn't matter whether it's 32 bits or 64 bits. And so I'm going to use Bitwuzzler for the rest of my evaluation. And then I wanted to check whether I can verify the correctness, so I manually fixed the broken division operator and looked at the 32-bit version, but unfortunately I run into a timeout of my SMT solver, so I cannot prove that it is correct, sadly. Then there are a few, but yeah, the verification succeeds if we don't try to verify it for the whole floating point range, but only a very, 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 very small range. Then I can show that the range analysis is correct for the division operator. And aside from division, there are of course other operators which you looked at, and for less than equal and less than, I can show that they are correct, which is not that exciting, but still better than nothing. And for the other, either I run into timeouts or internal errors in the one model checking tool. Then I was thinking maybe I just have to give more than 8 hours, maybe 48 hours, maybe 48 hours enough time to find it correct, but yeah, still not the case. Either I run into memory or timeouts. And then we have the 3 older commits with non-vulnerabilities. And what is pretty nice, if we run it on those vulnerable commits, we immediately, in less than 5 minutes per commit, we can refine the vulnerability, which is pretty nice. And then we have some synthetic commits. So we introduced bugs into the division operator, which did various broken things, and looked at the 32-bit version of it. And yeah, again, my tool can find all those obviously broken test cases. And I can detect different types of vulnerabilities. So one vulnerability type is like not accounting for a number, not accounting for -0, or just computing a wrong range result. And this gives at least a bit empirical evidence for the correctness of the main operators, because for all the edge cases, my tool finds a solution in less than a few minutes. And if it doesn't find a solution in like 48 hours for addition, it's likely that addition is correct. Now, again, this is not like a formal argument, so, but it's like an intuition. And for my research question, yes, I can find new bugs. I can find all the old bugs. I can find all my synthetic bugs. Correctness, I cannot really prove aside from the 2 functions. And if you are also working with SMT solvers, I can highly recommend Bitwoozler, which is the fastest across my testing. And yeah, 2 takeaways: finding bugs, and if you have simple operations, it works well. But if you have complex floating point stuff, it remains a big challenge. So, conclusion. This is, at least as far as I know, the first direct formalification of, or attempt of V8's range analyses. I needed minimal source code verification. Like in many papers, if they try to prove such range analysis code, they sometimes extract the original source code and translate it into another language, which it's easier to verify. But if you translate from your source language to your target language, you can also make like mistakes during the translations. And this is something I successfully could avoid. I still had to do some minimal source code modifications, but the source code modifications were unrelated to the range analysis itself. Exactly based on the counterexamples, I then created this pipeline which automatically generates JavaScript proof of concept. And some technical achievements: I enhanced ESBMC, which is an academic tool. And if you throw an academic tool at software like V8, there are all kinds of places where it just explodes, because it has never been tested with those parts of the C++ standard. And so I enhanced ESBMC a lot. I verified my pattern-based approach, and because I believe a lot in open source, I contributed most of my work back to ESBMC, 2.5k lines of code and 40 plus PRs, and I'm still contributing some of my fixes. And as for the real-world impact, I found a new bug in V8 range analysis, and I demonstrated that it's indeed practical to use formal methods on complex C++ code. Now, again, formal verification or model checking is not like your magic tool which you can just throw at your problem. You have to, in the best case, you have like very self-contained functions that are not that huge, maybe 500, 2,000 lines of code. But in that case, form verification can be an interesting tool to automatically find bugs. So with that, thank you for your attention.
We have 5 minutes for questions if anybody has any questions. There's something over here. Okay.
Maybe I missed it and you said it, but did you run your verification on the patched division operator? And did it succeed, or did it run out of memory for the patched operator?
They didn't publish an official patch, like it's still unpatched. Because
okay, sorry, then I missed this part.
To trigger the bug, you have to use some experimental flags, and so they didn't patch it yet.
But would you guess that, like, if this was also patched, then it would be like for multiplication and addition and so on, that you run into resource limits?
Probably.
Okay, because I was wondering, like, everybody who did this for other things always had trouble with the division operator, so I was kind of...
Yes, division and multiplication are always problematic.
One more question? Okay, well, Simon, that was absolutely brilliant. You've left us on a cliffhanger before lunchtime. Enjoy your lunch, refuel, and we'll see you back here at 2 o'clock. Thank you very much. Thank you so much.